We start section 3.2, that's paths and circuits in a graph theory problem, by looking at what is probably the most famous problem in all of graph theory. And in fact, it's actually the problem that kicked off graph theory in the first place. Graph theory is a relatively new field. It only popped up in math a few hundred years ago. And I think it's believed that this is really the question that got it started, that motivated graph theory to be developed into this field. So we have this town of Königsberg. This was a real town. I think it's called something else now, but it's separated by a river. So that's, just to be clear, this here is our river, right? This blue part's the river. And so you've got sort of two banks, an upper bank and a lower bank. And in the middle of the river, there's these two islands. And connecting the upper bank, the lower bank, and the two islands are 7 bridges. So the question is it possible to take a walk in this town so that you cross every bridge once and only once? That's what motivated this graph theory in the first place. So it doesn't really say where we're starting, and it doesn't even necessarily say that we have to end in the same space that we started from. So I guess we can just sort of start guessing and checking. Maybe you start up here on this north bank and you go over the bridge into A, and then you go over the second bridge into B. Now we only want to cross every bridge exactly once, so let's come back up to A, and then back up to the north bank at C. Then maybe we can come down to D, that's our only choice, but now we see that we have a problem. Because if we were to try to cross this bridge to get back over here, we're going to get stuck. We've run out of bridges. We can't really leave A once we go over that bridge, but the same is true if we go over this bridge labeled F down to the lower bank. There's no way for us to get back to this last bridge here. So it doesn't seem like it worked that time, but maybe we just started at the wrong spot. Maybe we should have started somewhere else. Let's say we started like in the middle here. We started on the middle bank, maybe that's where we live. Maybe I would do something like come down to the lower bank, come up to this second island, and maybe right away I'll go over onto bank, or into the first island again to get this bridge out of the way. And then what? Well, I could go up, and I could either come back down to D, but I'm going to get stuck because I've run out of bridges, or I could come back down to A, and then down this bridge over to B, but again, I'm stuck because I've run out of bridges, and I've missed this one. So you can play around with this for a little while, but you'll find that there doesn't seem to be any way to do this right. There doesn't seem to be any way that you can cross every bridge exactly once. If you are allowed to cross bridges more than once, sure, but doing it once and only once seems impossible. And so a natural question that we could have now that we've been introduced to graph theory is, how can we sort of turn this into a graph theoretical question? And so oftentimes what we'd want to do is come up with some way to represent this map, which I've scribbled all over, using a graph. So given the fact that these bridges are connecting one landmass to another, it makes sense that the bridges would be the edges in a graph, and the landmasses would be the vertices. So I'm going to have 1, 2, 3, 4 vertices, our north bank C, our first island A, second island D, and our south bank B. And I'm going to draw a bridge, or draw an edge for every bridge. So there's 2 bridges connecting the north bank C to island A, which means I actually need 2 edges here. Now this is a little bit weird. We call these multi-edges because there's more than one edge connecting the same pair of vertices. That's fine, there's nothing in graph theory that rules that out. It's just a specific type of graph. Similarly, there's 2 edges connecting A to B because there's 2 bridges connecting A to B. There's just 1 bridge connecting A to D, and just 1 bridge connecting C to D, and 1 from D to B. So this is what the graph looks like. And what I want from this graph is I want some sort of a way to go from vertex to vertex along the edges so that every edge gets used exactly once. Right, remember, edges are equal to bridges here. And I want to go from vertex to vertex in some sort of way so every edge gets used exactly once. Now you can play around with this graph the same way we did with the map and find that it's really hard to do that. So we'll see why that is in just a few minutes. In the second problem here, we have the following table tells us which flights between various cities in a region of the US, or it's phrased weird, a traveling salesman needs to visit every city is it possible to plan a route starting and ending in Baltimore so that he doesn't visit any city more than once? And again, you could try to play around with this here and say, well, maybe I go from Baltimore to Boston, and from Boston to New York, and then from New York to Buffalo, and just sort of do guess and check here. But this is a natural type of problem where we would want to model this with a graph, because we have all these various cities, those would be our vertices, and then we say that they offer flights to particular or in between pairs of cities. So the flights that are offered would be a natural choice for the edges. So let's build this graph over here. We have Baltimore, we have Boston, we have DC, Buffalo, we've got New York, Providence, and Erie. Okay, and so we're going to draw an edge if there's a flight between that city and another city. So there's a flight from Baltimore to Boston, DC, Buffalo, and New York. Boston, DC, Buffalo, and New York. There's also a flight from Boston to Baltimore, then New York, Providence, and DC. So New York, Providence, and DC. And there's flights from DC to Baltimore, Boston, New York, and Erie. So New York and Erie. Then there's flights from Buffalo to Baltimore, to New York, and to Erie. Then there's flights from New York to, let's see, we already have Buffalo, DC, Boston, and Baltimore, so we've already drawn all four of these edges. Then we've already drawn the edge from Providence to Boston, and from Erie to Buffalo and DC. So this is a complete graph that matches this scenario. And so what do we want here? We want to find some sort of a path for this salesman that starts and ends at Baltimore, because that's where he's from, and we want to visit every city exactly once. Now, we don't have to do every edge exactly once, right? This is different from what we did in the first problem. In the first problem, we wanted to traverse every edge exactly once. Now we just want to visit every city, every vertex exactly once. And again, you could try to play around with it, maybe go from Baltimore to New York, to Buffalo, to Erie, to DC, to Boston, to Providence. But this isn't going to work. And actually, this vertex right here, this is going to cause you problems. No matter what you do, at some point you're going to have to visit Providence. The only way to get there is through Boston. So you start going for your little walk here, or you're visiting your different cities, whatever you do, you'll hit Boston, then you'll hit Providence, and then you're stuck. The only way to get anywhere else is to go back through Boston again and to reuse that Boston vertex. So the only way that he can visit Providence is to visit Boston twice, which is not what we want. Okay, so in both of these problems, we're looking for specific types of paths through our graphs, or walks through our graphs. And so let's go through a couple of definitions here. What is a walk, or a path, or a circuit? So we say in a graph that a U to V walk is just a sequence of vertices in a graph such that consecutive vertices are adjacent. Remember, adjacent in a graph means they're connected by an edge. So a walk from U to V just means starting at U. I don't have any U here, so maybe an A to B graph, or A to B walk would be start at A, go to a sequence of adjacent vertices, and land at B. Okay. Now, if the endpoints are the same, like if U, in this case, in our definition, this means if the starting vertex U is equal to the ending vertex V, we would call that a circuit. So let's go through a few examples here. So I had mentioned that we could have as an A-B walk the path A-C-E-D-B. And I'm just going to list these. You could put commas if you wanted to, but I'm just going to list them in a row. This is saying go from A to C to E to D to B. Right? That's a walk in our graph. Another A-B walk would be a simpler one. Just go straight from A to B. There's an edge between them, so that counts as an A-B walk. Something that I couldn't do for an A-B walk is I couldn't do something like A to C to E to B. right? That's not allowed because there's no edge connecting E to B. Okay. Now a circuit is just a graph or a walk that starts and ends at the same vertex. So for example, an A to A circuit might be something like A to C to B to A, right? A to C to B to A. So circuit just means you start and you end at the same spot. And notice that in this case, there's nothing that prevents you from repeating vertices here. Nothing in the definition says that you have to visit every vertex only once. So I could even have the A to B walk consisting of, let's see, A, C, E, F, G. So I've gone A to C to E to F to G, then back to E, back to C, and back to A. This works. This is allowed. You're allowed to repeat vertices if you're just taking a walk in your graph. But we saw in the warm-up that sometimes it's useful in certain contexts to look for a walk that has the property that you're visiting every vertex exactly one time. Okay, so we'll talk about that on the next page. Now, if we're trying to walk from one vertex to another, in this graph here, it's always possible, right? For any vertex that you start on, you can get to any other vertex through a walk, right? Pick any two vertices, there's going to be a walk between them. That means that this graph has the property of being connected, right? It doesn't mean every vertex is attached or adjacent to every other vertex. It just means you can get there through a walk. So we say that a graph is connected if between any pair of vertices there is a path. So as an example, okay, well this one up here, this is connected. Something like this would be connected. But a graph that's not connected is one where you could find a pair of vertices where there's no path between them. Right, so this graph here is a non-connected graph. This is just one graph and it's not connected. Maybe I could even add something like this, right, just a vertex floating on its own. There's no path that's going to get you from, let's label our vertices here. There's no, let's say, B to E path. Right? There's no path that's going to allow you to get from B to E because these two components are not connected. So we say this is a disconnected graph, and we say that it has three components. Namely, the components are this part right here, the AB part, the C on its own part, and then this triangular part here. So this is a disconnected graph with three components. Okay, now, we're mostly going to talk about connected graphs here because if we're looking for that special type of walk where you visit every vertex exactly once, you're not going to be able to find that if your graph is disconnected. So from here on out, we're mostly talking about connected graphs. Okay. So that graph we were looking for in the warm-up, where we were walking around the bridges of Königsberg and we wanted to cross every bridge or every edge exactly once, we would call that an Euler path. I'm just going to make a note here. This is pronounced Euler, right? Not Euler, not like Bueller. So an Euler path, or sometimes called an Euler trail, is a walk in a graph such that every edge is used exactly once. And an Euler circuit is just a special type of Euler path that starts and ends on the same vertex. So if we look at some examples, you can see that some graphs have Euler paths and others don't. That Königsberg graph probably doesn't, or it seems like it doesn't. We weren't able to find one. But if we played around with these other graphs for a little bit, we would find that some of them have Euler paths, some have Euler paths and circuits. A circuit is an Euler path. And some don't. Some have neither. In this one here, this works. So I could go start in the lower corner. We'll use a different color so it's easier to see. Then go up and go to the roof of this house here. Maybe come back down across the diagonal, up to the other corner, across the top, down, up to the middle, down to the corner, and over to the edge. So we started here and we ended here. We can see from the way that I highlighted it that we didn't cross every edge exactly once. So this is an Euler path, but it's not an Euler circuit because I started at one vertex and I ended at another. So this has an Euler path, but not circuit. Okay, Now what about this second graph here? We could play around with it a little bit, we could try. So maybe start up here, come down, over and up. Maybe try to repeat that again, come down. But here we're gonna have a problem. So we can't come up here and use this last edge, or over here and use this last edge without getting stuck and leaving one edge out. So this is an example of a graph that has neither. It has neither an Euler path nor an Euler circuit. This one here, let's go back to pink. Let's see what we can do here. I'm gonna start at this vertex, come up and down and across. And I'm gonna try to, oh yeah. Let's maybe, well, we have to be careful here because I was tempted to come back up here, but if I were to try to come back up to this corner that I started in, I'm gonna run out of edges. I'm not gonna be able to leave again. So I'll leave this edge for last. Okay, so I come back down, maybe go around the triangle at the bottom and across, come up, and finally back up here. So in this case, my starting and my ending point were the same vertex, and I crossed every edge exactly once. This makes this an Euler circuit. If it has an Euler circuit, it automatically has an Euler path. That path is that circuit. Okay, and so in this last example, we can try again. We have, let's see, right, I don't know, we start somewhere. Maybe we'll try to start here and go up around this triangle and maybe the other triangle as well. Come across and down and over. I see already I'm gonna have a problem because if I go up, I'm stuck. If I go up and across, I'm stuck. So this is another example of a graph that doesn't have an Euler path or an Euler circuit. Right? And you could try some more and make sure that it wasn't just a bad decision on my part, but that actually it didn't exist. And the question is why? What do all of these graphs have in common? So I'm going to give you a minute to try and play around with it. In the notes, there's this graph, and you can start playing around with it yourself, maybe draw some examples, and see if you can figure out what makes a graph have an Euler path or circuit.